All right, welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Linear Algebra 1. This is Chapter 4, which is just the generalization of Chapter 3 when we do these geometric vectors in 1 dimension, 2 dimension, 3 dimensions. Now what we're going to do is just get the vector space Rn, which is arithmetic vectors that have n coordinates now, not just 1 or 2 or 3. Where are we going to get these coordinates from? Linear combinations in a basis, so we'll get at that, but that'll be the next video. Today what we're going to do specifically is just define what this vector space is and give some of its more basic properties. Let's get to it. All right, first what we're going to do is define, this is Noodles, he wants to see what's going on. It's snowing out, it's blizzarding outside right now, so everyone's inside, even Noodles. All right, what's that? This is the set of all arithmetic vectors. What is it? Essentially, it's a column vector which has n coordinates. Each of these coordinates come from the set R, right? Yeah, okay, go. That's all you need to do. That's the set Rn. This is what we're going to call arithmetic vectors. And just like we did last time, once we had coordinates, when we did this painfully in the last chapter, we did the basis for a line of vectors, a basis for the space plane of vectors, and a basis for the space of vectors. Now what we're going to do is essentially, once we had coordinates, we say that an addition is coordinate-wise and scalar multiplication is coordinate-wise. It's the same thing here. What do we mean by coordinate-wise? When you add two column vectors or two vectors in the space Rn, then we're just adding them coordinate-wise. So you add the first coordinates together, you add the second coordinates together, dot, 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 you add the nth coordinates together. And when we scalar multiply, when we dilate or contract vectors in dimension n, whatever that means, when we're in dimension n higher than 3, we still just scalar multiply each of the, or the scalar goes onto each of the coordinates. So this is the set Rn, and this is the operations addition and scalar multiplication on Rn. What we're going to try and do is turn that rigorously into a vector space. What do I need next? First of all, we have a set of new objects. I have a way of defining addition, and I have a way of defining scalar multiplication. I want to know when things are equal. I want to know who the zero guy is. I want to know who the negative of somebody is, and then I want to get all the properties and wrap that together. So that's where we're going next. All right, two vectors x and y. I'm going to suppress column vectors, but they're always column vectors. Some books also will mark, in his textbook also points out that some notation, they lay it down. Mostly this is convenient because in our textbook in English, we write left to right and on lines this way. But if you're in Chinese, it would actually be quite convenient to make them column vectors because you're going to be doing right to left and then the vertical columns. But when we type stuff, it's more convenient to lay them down. But when I want to, in chapter 5, start viewing these as points I'm moving around in space with linear transformations, which is the same thing as multiplying on the left by a matrix, we'll get there in chapter 5. Matrix multiplication is defined if the inside indices match, so I need this to be an n by 1 vector, n rows, 1 column. So it's a column vector, 1 column, n rows with these entries. So given two vectors, which are column vectors, these things, we have this new set of objects called column vectors. The first thing you want to know is I better have a definition, or when are things the same? So two vectors are called equal if and only if all of their coordinates are equal. So x1 has to equal y1, x2 has to equal y2, and all the way down to xn has to equal yn. This seems like an obvious definition, but it's when we start getting into algebra and start comparing things and doing theory that we would say this thing has to be equal to this other vector, and then when is that true? If all the coordinates are equal. And we already did this essentially in one of the previous videos at the end in section 3.6 when I looked at arguing why these vectors could never be multiples of each other. Because we said, well, if they are, then this one has to equal this one. And when are those equal? Only when all the coordinates are the same. But then you get alpha as 1 and alpha as -3 at the same time. And this is ridiculous. So this is how we use this. So regardless now of what dimension you're in, vectors are equal if and only if all the coordinates are equal. And we're going to write this as we normally do. The other two things that we need before I can just show that this is a vector space is the zero vector. The zero vector in any dimension is the vector that has all coordinates zeros. And the opposite, or the negative of, or the antipodal vector of a vector, or the additive inverse, whichever one you want to call it, opposite is good enough, is of a vector x, is the vector negative x, which is now a symbol. It's not -1 times x, it is, but we have to prove that it's a property. So negative x is the vector which has the same absolute value of all the coefficients, but they're all the negatives. So negative x will have all the negatives in there of the original values. given these guys, the zero vector, the opposite vector, and equality, we can now show that this vector space Rn with addition, scalar multiplication, the zero vector, and the number 1, in fact, forms a vector space over the real numbers. Let's do that. All right, theorem, these are all essentially deducible things. We can prove each of these statements, but we have these properties. That's why they're properties and these not axioms technically. But we've constructed this set of column vectors, which we call Mark wants to call the arithmetic vector space of column vectors. Then we defined addition of vectors, which is coordinate-wise, and scalar multiplication of vectors, which is coordinate-wise, vectors with a scalar. Then we have the zero vector, which we just saw, which is all 0 entries. And then we have the number 1, which I'm hoping you're reasonably familiar with. With these guys, the set of all n-dimensional arithmetic vectors, addition, scalar multiplication, the zero vector, and 1, we have a vector space over R. What that means is we have the following 10 properties. What are they? By construction or by definition, we know that I'll use x and y. If I take vectors, x plus y is always already in Rn if x and y are in Rn. So we have closure of addition. Then we ask ourselves, well, does it matter whether I do x plus y or y plus x? No, it turns out it doesn't matter. So this will be additive commutativity. X plus y is equal to y plus x. You can flip them around, it won't matter. Then we have to ask ourselves, was there a guy 0 that left everybody alone? Yes, there is. There exists, oh, I'm using fancy, there's backwards E. There exists, there is 0 with 0 plus x equals x for all x, which also equals x plus 0, but I don't have to write that down because it's already true by this axiom. So 0 leaves everybody alone using addition. As soon as we have the 0 guy, we say, is there somebody you could add to x which would give me 0? Yes, the opposite. There is for x. We have negative x with x plus negative x equals the 0 vector. And then what's the last one that we need? I forgot it. It should have been number 3, but the order doesn't really matter. I got excited about the 0 vector, but you should move down one, zoop, zoop. And then when you add 3 things at a time, doesn't matter whether you start at the front or the back. No, we have additive associativity. So x plus y plus z is also equal to x plus y plus z. So this is additive associativity. 5 things about addition alone. Then we have scalar multiplication. We have a few properties about just the scalar multiplication and then how to mix them. So the next one is when I scalar multiply vectors in a column vector with n coordinates, is it a column vector? Yes. K times x is again in Rn. This is closure of scalar multiplication. If and when we do subspaces in the section where we do subspaces of Rn or subspaces in a general vector space, you have to have all of these 10 axioms satisfied. But if it's a subset of Rn, it already satisfies all of these ones inherently. So then what it has to have always to be a subspace is closure of addition and scalar multiplication. So number 1 and number 6 actually in later deeper theory actually become extremely useful. And then what do we have? If I had k and l, can you do k times l times x? And is that the same as doing KL times X? Yes, it is. So you can associate the scalar multiples. Then what you can do is we're going to have 2 distribution properties. If I have 2 scalars, I can have K plus L, and then I can have a single vector. What that's saying is if I add 2 numbers and then scalar multiply X by that sum of numbers, is that the same as scalar multiplying that vector by K and then scalar multiplying that vector by L? And then adding those as geometric vectors. Can I do that? And yes, it says you can distribute. So we're distributing a vector onto 2 scalars. And then the other property is going to be, what if I have 1 scalar and 2 vectors? Can I do that? Can I add these column vectors, then scalar multiply them? Will that be the same as if I do scalar multiply x and scalar multiply by y? And then add those vectors? Yes, it is the same thing is what it says. And then there is a number 1, which when I scalar multiply, leaves everybody alone. With these 10 things, we can see that we indeed do have a vector space over R. So This is our vector space. Let's do an example, and then I'll do 3 more useful properties in a theorem about negatives and zeros. Actually, and because these are all properties, these are extremely easy to deduce. So say the property about does 0 plus x actually equal x? How do we prove this? So I'll just do one quickly. Proof. Well, what do we know about this? 0 plus x is going to be 0, 0, dot, 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 0 plus x1, x2, dot, 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 xn. We know by definition of this addition that it's coordinate-wise, so that should be 0 plus x1, 0 plus x2, dot, 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 0 plus xn. And then we know by the properties of real numbers that 0 leaves every real number alone, so this will be x1, x2, dot, 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 xn, which is in fact, who is this guy? That is x. So 0 plus x is equal to x. This is how we prove these. It's usually, they're not too bad. They're not axioms because we're not taking it on faith or assuming them a priori. Basically only using the definition of a few previous things like addition and scalar multiplication. They should mostly just fall out of this. All right, now let's do an example. All right, so example 1, I've got 2 vectors which are in R4. This is going to be 1, minus 1, 0, 2, and then I have 2, 1, 3, 4. And then I've got a couple of scalars, specifically 2 and 3, and then it shows you, instead of using all this mumbo jumbo, I just want you to get your hands dirty. I'm going to do it for you, I guess, but you can try with other ones. Anytime you get all these properties, this is what you should do. Pick a couple numbers, pick a couple of vectors, and try to see if that works out. If it does, try to see why they assume that they can prove it in general. They're just switching from calling these specific numbers to x1, x2, x3, x4, and then see if it all works. How do I do the first one? I want to show commutativity. So the easy way to do that is just to compute when I actually have numbers now, x plus y and y plus x using the definition, and we'll see that they actually are the same thing. So what am I going to get? X plus y is going to be the vector 1 minus 1, 0, 2 plus 2, 1, 3, 4, which is equal to, by the definition of addition, 1 plus 2, negative 1 plus 1, 0 plus 3, and 2 plus 4. Which is actually, if you want to see how they prove it in general, when it's x's and y's, and I can't do this when the numbers, because of the commutativity property of the numbers on the inside now, I can write that as 2 plus 1, 1 plus negative 1, 3 plus 0, 4 plus 2, which is in reverse equal to the definition of what? 2, 1, 3, 4 plus 1 minus 1, 0, 2, which is equal to y plus x. So that's the strategy of how you would do it. And now you can see, by seeing that cleverly, it didn't matter what those numbers were, I can just write them as x1, x2, x3, x4, y1, y2, y3, y4, and it won't matter if you cleverly just put the coordinates in, flip them inside by the definition of commutativity of real numbers, and then re-separate them. This is why x plus y equals y plus x for all of them. I know what you wanted to see was this, x plus y equals 1 minus 1, 0, 2 plus 2, 1, 3, 4, which is equal to, by coordinate wise, this should be 3, 0, 3, 6. And then what's y plus x? Y plus x is equal to, y was 2, 1, 3, 4 plus 1 minus 1, 0, 2. And then adding them coordinate wise is going to give me, guess what? 3, 0, 3, 6. So they're the same vector, check. But if you see how we're going to do it, it didn't matter what the coordinates were, it works for all of them. Then how am I going to do this k plus l business? Same thing. What you probably want to see is what's k plus l then? 2 plus 3 is 5. So if I do that first, what is 2 plus 3 times x? This is 5 times x, which is 5 times what is x? 1 minus 1, 0, 2. Which is coordinate-wise, which will be 5 minus 5, 0, 10. And then what do I have to do to get that on the other side now? What they're saying is, if I do 2 times x plus 3 times x, that's going to be 2 times 1 minus 1, 0, 2, plus 3 times 1 minus 1, 0, 2, which is now I do scalar multiplication twice. Okay, I will. This will be 2 minus 2, 0, 4, plus 3 minus 3, 0, 6, which is going to be 2 plus 3 is 5, negative 2 plus negative 3 is negative 5, 0 plus 0 is 0, and 4 plus 6 is 10. And and we got the same vector. This works. It works for everyone. What you should try now doing for yourself as a student is switch from using 2 and 3 and realizing that they don't matter, and flesh through and prove the rest of those properties using K and L and X and Y and Z. All right, now here's the more useful things, especially like this one and a couple of these other ones I think we're going to use in the next section when we talk about linear independence, span, basis, and dimension. Hold on to your hats for that one, but it'll be a little bit better than having to do it case-wise. What's the basis of a line? Any vector in the direction of that line that's correct. What's the basis of a plane? Any 2 non-collinear vectors. What's the basis of space? Any 3 non-coplanar vectors. Now it's going to be, a basis is you have to be linearly independent and span the space. So we're going to get new definitions, but this one specifically we actually will use to prove a few properties. This is saying scalar multiplication of a vector x by the number -1 is the opposite vector of a vector x. And so it's not hard to prove, but you do actually have to prove it. So theorem, let x be any vector in Rn, let alpha be any real number. Then if we have alpha times the 0 vector is not going to dilate the 0 vector in any direction or way, shape, or form, all you're going to get is the 0 vector again. And if I take the scalar 0 and multiply it by x, what is that going to do? It's going to multiply each coordinate by 0. I'm already proving it. And then that's going to be 0 in each case, because 0 times any real number is 0. So then it'll create the vector with all zeros, which is the 0 vector. And then, like I just said, multiplying x by -1 is the opposite vector of x, is what that's saying. The additive inverse of x is -1 times x. And more importantly, what we need this for is if you somehow have in some derivation or proof that you're trying to do or homework assignment where you get where they say a number times a vector is 0, then that immediately tells you that either alpha is 0 or the vector is 0, the 0 vector. You can't have any other scenario. At least one of these are true. You can't have this is not 0 and this is not 0 and somehow multiply it to get the 0 vector. That will never happen. So these are the most important properties. More importantly for the video, please subscribe right there. I'll see you next time.